Hey guys,
Hello, Matt.
can you guys hear me well?
Yes, all
Nice.
okay.
Хорошо. So we will wait like 5 seconds, 5 minutes, and we will get a small revision and an exercise, and then we will get through the quiz. Okay? Just to
Okay.
confirm, you
And
guys
what?
see the quiz on the Moodle, or you cannot see it? Please tell me you cannot see it.
Hello, Professor.
Hello, Zuhair Abbas.
How are you?
I am very good. I see that you are so smart that you finished all your lectures, and now you're taking more lectures, huh?
Of course, bro. I'm just here for you.
So I see that not a lot of people are on time today. Last time there was like 23 students already, even before the lecture started. Huh?
In Matt, there is no quiz in Moodle.
Ah, that's good news. That's great news. That's nice. So how are you guys? How did you find the first lecture?
It was interesting.
It was interesting. Nice. Thanks for the information, bro. How about the others?
Lectures are very good, actually. I'm really satisfied. I'm really like
Ah,
thank
nice.
you very much for your time and your efforts.
Thank you. So I received a lot of questions during the week about the lecture. So if you guys have some questions, or maybe I didn't answer your question during the week in like text very well, you can just ask right now any questions you have.
I have a question, but it's not about lecture, it's about homework assignment.
Uh-huh.
Do we need to do some visualization of results to show like how bad our model and how good VGG model?
So
Or
basically,
it's not
yeah.
it's not mandatory.
Yeah, the last part, which is the optional part, this is where you just can play around and do whatever you want. So basically, you can do any type of visualizations that you see good. You can go through for example, the samples which were not correctly predicted. You can try to interpret, well, anything you want. So basically, it's an optional part where you are allowed to do anything that you find interesting. And depending on the effort made, you're going to get more points. And points are not just in the within the what is it called, within the homework, but they also can be used in, for example, in your exams and stuff.
Get it? Thanks.
Any other questions?
Good morning. Oh, good afternoon.
Good afternoon. So just to confirm, who was the person who was going to be late for the...
Mustafa Ayman.
Nice. Is he here?
I don't know.
Let's check. Mustafa. Where is he? Yes, Mustafa Ayman. Mustafa Ayman, I see that he's not here with us. Nice. So do you guys have any other questions? Maybe some examples or some...
I guess not. I guess no.
So I will prepare a small exercise for you guys to do. So basically, one of the students, by the way, we're going to continue using Zoom. So this is, we decided to just continue using Zoom. Microsoft Teams is impressive, but it just has a lot of functionalities that will just, too complicated. So let's just stay with Zooms. It just has pictures of people and just audio, and that's enough for us, right?
Imad, what
yes.
about the plan for today? Like we have two lectures, and when we have like our some kind of 30 minutes conversation on us.
Discussion.
Yes.
Well, however you guys want, we can discuss for as long as you want.
Okay.
Nice. So I think for the discussions that we chose to do for like after the sessions, I will see with the participants of the course if one of you guys have any information that he would like to share or some small presentation that he would like to make, some sharing his experience or stuff like that. You can feel free to use these 30 minutes for that. For now, what we will do is go through the lectures again. Just read the lectures, just small summary or revision. And then we will go to an exercise, which was sent to me by one of the students. I think it was, let me check, who was it? Marina. So yeah, basically Marina sent me one of the resources that we had. And she went through the examples in the resources and she found that there was an error in the resources. So basically we will go through the resources together and spot the error and solve it, right?
Spot the error and blame the researchers.
Spot the error in what?
And blame the researchers.
Yes, of course. That's fine.
Perfect.
Then, this is Maxime, sorry. This is my name. Nice. Let's exit the quiz. Sure. This is for interpretive machine learning. This is for image classification. And let's start sharing the screen.
So can we start the quiz?
Not the quiz. So sadly, some of the students cannot make it in time or at 5. So we will wait a little bit for them to arrive. In this time, we will make a revision and an exercise, and then we will go through the quiz. The quiz I will give you around like 15 minutes. It shouldn't take you more than 5 minutes, but it's pretty simple, just basically true or false, and it's very basic questions, okay? So it's just something to get your marks up.
The quiz will be regarding classification and your second lecture, right?
Yes, exactly. So basically, the things that we will revise right now. So just to be prepared. For some reason, I'm sharing the wrong slide. What are you guys seeing?
Black screen.
Black screen.
Yes.
For some reason, Zoom is not allowing me to show the correct screen.
Maybe Zoom is not in favor of quiz.
Zoom is not what?
In favor of quizzes.
Yeah. Can you guys see the lecture now?
Yes, but just a
Yes.
portion of the screen.
Now see the lecture, now black screen, right?
We see the lecture and Savik what we don't need to see. Some
screen.
What do you guys see?
You.
Ah, that's the thing that you guys don't want to see.
No, I see like the Chrome window.
You
With
can
the
check
slides.
in Telegram.
Хорошо. Nice. So you guys can't see the quiz? Just to make sure, because I have the answers right here.
If you share the answers, then we can see the quiz.
Let's share the screen. Now I hope you guys cannot see anything, right?
yes.
Хорошо. That's nice.
Just the answers. Yeah.
So the first lecture was about image classification with CNNs. And in this lecture, we spoke about first what are neural networks. We went
Не-не-не. Чё?
Квиз. Оно же где-то есть?
Ну, он на Moodle есть, просто он пока скрыт от вас. Что?
Can you off the microphone,
Yep.
Nikit, please?
Muting the participants.
Imad, please continue.
Nice. Everybody's muted? Хорошо. So basically, in the first lecture, we spoke about neural networks in general, spoke about convolutional neural networks, and then we spoke about the different layers that we had in neural networks. The first part was speaking about what is classification, what is regression in general. So we saw that classification is about detecting stuff such as dogs, like the digits, And for regression, we try to predict stuff such as numerical values like age, price, and temperature. We saw linear regression, which is a method of mapping a continuous value into another continuous value. And then we saw how logistic regression is like an interpretation of linear regression, but how can we use it for classification? And we saw that we do this task by adding a activation function. We also saw that right after that, we saw that perceptron, which is the basic neuron of a neural network, is nothing but a logistic regression. So basically, it's a multiplication of the inputs with a trainable weights, adding a bias, summing all of it together, and then passing it through an activation function. We saw that the first type of neural networks was called multi-layer perceptron, and that is just adding or stacking a set of perceptrons in the same layer and then stacking a set of layers after each other. We saw that adding a lot of neurons in each layer and adding many layers can lead to overfitting, and hence usually you should start by training a small neural network and then increasing the size of the neural network as you are going ahead. The second part was speaking about convolutional neural networks in 2D. So we saw how convolutional neural networks operate, which is just a kernel of trainable parameters that walks through the image and just performs the same operation of multiplication and addition to give us the output. We saw that this method of doing computation is better than fully connected neural networks, especially for images, because it computes less parameters, and the parameters are shared between different parts of the image. So if the face of a cat was in this area or was in this area, the parameters that we are learning or we are training are definitely going to learn from that face of the cat. So whatever the face of the cat is inside the picture, the parameters will get to train on it. We saw that there are several techniques for helping neural networks, which are padding and stride. So padding is used to maintain the same size of input as the output for convolutional layers, and stride is basically the jump size of the kernel. So basically, in this case, we are moving with 1 pixel at a time. And if we have a stride of 2, we will jump 2 pixels at a time. The dimensions of the output are as follows. So the number of input in plus 2 of the padding minus the kernel size divided by the stride plus 1. We saw that max pooling or pooling in general is an operation that doesn't require any trainable parameters, and it uses a filter of a certain size and stride and just goes through the image and takes only the maximum value in each square. The size of the output of max pooling is the same size of the output of convolutional layer. And then we spoke a little bit about convolutional 3D, and we said that it's applied for videos or MRI scans or for detecting, for example, the actions in videos, right? The only difference or the main difference is instead of having a matrix of input data, so just an image, we now have a big 3D box or 3D data set. Hence, our kernels will become 3D kernels that will also make a move in this third dimension, be it the time dimension, or for example, in MRI scans, then it's the Z dimension, right? So this is it for the first lecture. There's going to be, I think, 5 points in the quiz about the first lecture. The second lecture, was about interpretable machine learning. And we covered topics such as what is interpretability in general and what are the easily interpretable models. We spoke about one method for black box interpretation, and it's called BLIME. And we spoke about the third method, which is the most important one for images, called GradCam, right? So for interpretability, we saw that interpretability is a very important topic for multiple application areas. And one of the examples in here that we gave is understanding why neural networks are making why are they making their predictions, and why are they making their errors. And understanding this one can help you understand the biases in your neural network and can help you train better neural networks by changing your data or changing your training. So importance of interpretability. So we saw that interpretability is very important in different scenarios, mainly for scenarios such as medical applications or loans and stuff like that. We saw that there are 5 scopes of interpretability. First is algorithm transparency, and it concerns how the model is being trained. Global holistic model interpretability concerns how the different parts of, or how the inference is being made. A global model interpretability on modular level speaks about how each part of the model contributes to the inference. And the local interpretability for a single prediction speaks about how does the model, or why does the model make its predictions on this precise instance, whereas the final one is how does the model make its predictions on a group of predictions. We saw 2 examples of very simple models to interpret, which are logistic regression, which we will be using in Lime, and decision trees. We saw that logistic regression are very interpretable because the weights of the logistic regression have meanings. So the higher the weight is, the more valuable that feature is. The lower the weight is, the less valuable it is. And for decision trees also, we have the same ability to explain. So basically, if I want to understand why was a sample predicted in such a manner, I just go from the start of the decision tree and then walk through the decisions line by line and give you the final reason for the prediction. So for example, your age was more than 20, your income was small, and stuff like that. So basically you will give explanations why the decision was the way it was. Lime is the best model if you are going to be using tabular data or text data. And what it does is, so the name is Local Interpretable Model Agnostic Explanations. So simply what it does is it takes a very complicated model and it tries to explain its decisions only on a local manner. So basically, we take this sample, we look in its neighborhood and try to build a simple linear model that does the same work as the complex model in this small area. After we do that, we just simply interpret the small or linear model and then generalize the interpretations of the linear model into the bigger model, right? So the steps are very important here. So first we select the instance of the desired instance. We create new data just from randomly sampling or in the space of this data set. And then we classify them, we weigh them based on how close are they to the target point. And then we create a simple classifier inside this area. After that, we just simply, as we said, interpret or explain the predictions by interpreting the local model. How can we apply this methodology for textual data? So only thing we will change is we will change the we will change the text from a string like this into just a vector of existence of a word, not existence of a word, and then just kind of sample in this distribution of ones and zeros, or this vector distribution of ones and zeros, and just get different samples. And this will give you the black points in here, build a linear classifier, interpret the results, and basically you will get these feature weights, which are the importance of every word in that text for the predictions. So in this case, we see that the word channel is very, very important for detecting spams, because usually channels or YouTube channels and stuff like that, they always send you spam emails and stuff like this. So this is why the model picked up the word channel as a very indicative word for spam. Superpixels are a matter of creating spots inside the image. So basically, it's some sort of clustering for the image. We take this image and then we create these different superpixels, which will later on be turned off and on to give us this kind of vectors, but for images instead of text. And then we repeat the same process of Lime, which is just using that vector. We create a simple, easily interpretable model. And then we find the same way, we find the superpixels, which are highly important for the classification. And basically we end up with this kind of feature, with this kind of map around the image, showing you the important pixels for making the positive classification and the important pixels for making a negative classification. The final part was GradCam. So basically GradCam gives you a class-specific heat map. So we take this dog, and we ask the neural network, why did you classify this exact image as a dog? And it will give you this kind of feature map, right? So you can see that the feature map in here, the pixels or the, what is it called? The dimension or the purity of the image is not the same as the input image. So basically it's a little bit distorted. And this comes from the fact that we don't build the heat map on the input image itself, but we build the heat map, sorry, based on the feature maps of the final convolutional neural convolutional layer. So what we do is basically find or calculate the gradient all the way back to this to these feature maps. That would give us a what is it called? A matrix for each feature map. We then summarize each matrix into one value, which using just the mean of this matrix. And then we compute the weighted sum of these feature maps with their corresponding importance. We can think of it as just the importance of this feature map for this class. Once we build this weighted sum, we send it through the ReLU function, and this will give us the following heat map. As you can imagine, the size of the input and the size of the output of the feature map of the CNN are not going to be the same. So basically, the CNN is going to shrink the size of the image with each layer, and hence, in order to bring back this feature map to the same size, we just use upsampling, right? So just to go through the steps textually, we compute the gradients, which are computing the gradients of YC with respect to the feature map activations AK of a convolutional layer. The following way, we compute the alphas, which is the average of these gradients, and then we calculate the final grade map heat map just by computing the weighted sum or weighted combination of the feature maps based on their alphas, right? So this was the two lectures that we had before. Now we will go through the, I see Mustafa Ayman has joined us, nice. So now we will go through the example that that I told you about, where the author made an error in the calculations. I would like you guys to find the error in the calculations, correct it, and tell me, well, just it's an exercise that will help you with the quiz. So basically, yeah. Let me find the exercise and share the screen again. Do you guys have any questions so far about what we have just revised in the first lecture? First week?
No.
Nice. So here is the error, or here's the, okay, sorry, let's use, what is it called? No. 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 Let's go for it. Yes, now it's showing. I'm sure many of you guys already know what I was doing, right? So yeah, so basically the articles here in towards data science are usually just paid, or just you need a membership, and you can just bypass that by going through the incognito browser, right?
Just clear your cache. That's all.
Really, that works also.
Yes.
Ah, cool. So here is the first example. So can you guys confirm to me if the calculations are correct or not, based on the size of the output?
No.
Okay, so somebody said no, the size of the output is incorrect. Can somebody tell me what is the correct size of the output?
If the stride is 1, then it should be 1, 2, 3, 3 by 3.
If the stride is one,
No.
then the
No.
okay,
I'm wrong.
nice. Let's bring back the formula. Can somebody remind me what is the formula? Let's write it together.
It's I think correct size, because it's input size plus 2 padding minus kernel divided by stride and plus 1. So input size is 4 by 4. There is no padding. The kernel size is 3 by 3. So 4 minus 3, it will be 1. 1 divided by stride 1 will be like 1. 1 plus 1 will be equal to. So
Correct.
I think it's correct.
Yes.
But since the values are wrong, I mean, in the resulting, in the
Maybe I
result of the
didn't calculate
calculation,
it.
So
it's like
7,
3 plus
right?
7 plus 3 minus 2 minus 3 minus 1. Oh no, it's also no, it's also
So
correct.
basically 7 plus 0 plus 3, which is 10, minus 2, which is 8. Ah, no, sorry. Yeah, we continue. Oh, shit. That's too much. Too much math for me, guys.
3 minus 3.
I think second square from second column and first row wrong. I think.
Yeah, that's easier. Yes. So basically 7 plus 3 plus 3, which is 13, minus 3,
Minus
is 10.
6.
10.
Yeah, so it's 7. Yeah, so it's 7. This is correct. Now let's go to the next example. Now the next example, can somebody tell me if the sizes are correct? So this is 3D convolution. This is the first, so basically this is a cube, right? This is the first matrix of the cube, second matrix, third matrix, fourth matrix. And this is also our cube filter. So previously it was a matrix filter, now it's a cube filter. And are these sizes correct? So basically the cube size in the 3 dimensions, so basically it's a 2 by 2 by 2. Is this correct?
Yes, the size
Nice.
is simply
Exactly,
correct.
it's correct. I would just assume that the mathematics here are correct, right? Let's come here and check the 2D max pooling, right? Is this correct?
It's correct.
It's correct in which case?
Why
It's
it's called
stride
3D
2.
max pooling?
If we have 2 by 2 pooling with stride equal to.
Exactly. So if the stride is equal to 2, then this is correct. So basically 7, 3, 9, and 8. So this is correct, but only if the stride is equal to 2. Sorry. Now we have the 3D max pooling, and this is where the error comes from, right? Can somebody tell me first if the sizes are correct?
As previous,
Didn't hear you?
I think it's as in previous case.
As in previous case. Now just bear in mind that this is 2 by 2 by 2. And I would assume that the stride is 2, right? So can somebody tell me if these values are correct? So very quickly, you can do the math of maximum, right?
No, they're not correct. They're a mistake.
So this value should be?
Should be 7.
Nice. This value should be?
No, I cannot calculate this fast.
3, I think.
3, right?
3.
Yeah, I think.
Yeah.
So we basically take these two maps and take 2 boxes from each, right? So it's 3.
Yeah.
In this point, we are considering this and
Right.
this 4.
This one is correct.
So this one is correct. And now we take
8.
This is 8.
exactly. So this is a great one. This one,
3.
3.
nice. So basically, you got the job. Now, if I say that the that the model is not a 2 by 2 by 2, but it's a 3 by 3 by 3 with stride equals to 1.
9, always.
So 9, 9, 9, 9, 9. Nice. And here?
6, I think.
6.
6. Nice.
But where we go if stride equals to 1, then yes.
No. No.
If it's 3 by 3 by 3, it will be 8.
Yes. So basically,
Yes.
6. And this one is 6. The next one is 8 and 8, right?
Yes.
I just got a little bit confused about stride in this case. We have 4 layers in MATLAB. It's 4 by 4 by 4. Yeah. Why are we counting each 2 together? I know it's like might be obvious, but I just got confused.
That's a great question. So basically, the size of the first example we did, the size was 2 by 2 by 2 with a stride of 2. So we basically imagine this as a cube, right? And we take the 2 by 2 by 2 first cube in here. We move, we move, we move, we move, we move, right?
Okay. Okay.
Nice. So basically, we take these
Yeah.
2 and these 2 to get the top corner, and then we move it this way, right? So it was the 2 by 2 by 2. Now, in the case of 3 by 3 by 3 with a stride of 1, we take these 3 with these 3, and then we move, right?
Yeah, got it. I just got.
Nice. So I just wanted to make sure that this example was very clear for all of you guys.
Matt, may you please explain one more time about the 3 by 3 by 3 max pooling? We try one example one more time because I don't get how I
That's a
take
great
the numbers.
Yes. Let's imagine a 4 by 4 cube. Put a 3 by 3 cube inside of it, right? So the first top cube in there, right?
Mm-hmm.
So basically, it will take these 3, these, and these, right?
Okay.
And then we move it one step further, right? So basically, these 3, and these 3.
Mm-hmm.
Exactly. So this is how you get this point and how you get this point. This point is these 3, and these 3.
Okay. And then you mean like for first like output, like it will be like only the 9s, yes?
Yes, the first output will be all 9s because the 9, you see, it's part of all the boxes.
Mm-hmm. Okay, I get it. And next one, the biggest number will be 8, yes?
No, I want you to do the next one, please. Yes, go ahead and give me the output of the next one. So for these 3 first boxes, what is the biggest number?
In this 3 now, it seems like 6, yes, maximum.
Exactly. So 6. In here it's 4. We're still with 6, and in here it's 4. So we are still 6 is the highest. So this point should be 6.
Mm-hmm.
Next to it would be.
Next one will be 6 also because we have 6.
It's the same 6, right? Now in this 3 by 3,
we have I8 now.
Yes, we have an 8 here, so it's the highest. And the next one is
also 8. Okay,
also
thank you. I get it.
Amazing. So
Thank you.
I hope that everybody else can do it easily. Everybody understood?
Yeah, just a second. Like, what direction do we take? Like, what's the standard direction for calculation?
What do you mean standard direction?
Like for calculation, like left to right first or up down first? Or...
top left. Top left. Mm-hmm.
Yeah.
However
top
you
left too.
However you want.
Like, I mean, this will change values in the output here.
Not really, not really. So let's look at it simply. I want to calculate this point, right?
Yes.
This point. What I go to the same area here, take 3 by 3.
Yeah.
3 by 3, 3 by 3, right?
Yeah.
I want to calculate this point. Which 3 by 3 will I take?
Okay. Okay, sorry. Yeah, sorry for my stupid question.
No, it's an amazing question. But if you are like this, in the case where you have just 2 points, right? Now, if you have multiple points, for example, you have 3 points, 4 points, 5 points, then it gets a bit complicated how to process it. Imagine we had a point in the middle, and this was a 5 by 5. Where will you go?
5 by 5. If we the initial convolution will be 5 by 5. Yes.
Yes. So tell me if so. Let's draw something together, right? Let's draw it like this. So imagine we have this. So it's a 5 by 5 thingy.
Yeah,
The
so
output
output will be 3 by 3 anyway.
Yes.
3 by 3.
For simplicity, this point is for these three. This point is for these three, right? Sorry. Let me undo it. Yes, it's for these three. So it's simple. The outskirts are very simple. The one in the middle, though. What are the three that it belongs to?
From the 3 in the middle, like from 2 to 3, like in
Exactly.
the
So this one.
yeah, this one. Yeah.
Perfect. For simplicity, what you should do, put this point here and start walking slowly using the stride. So if we had a 2 by 2 like this, nice. Okay, let me clear everything. Imagine we have a 2 by 2 in here, and we have a stride of 2. Can you tell me what this point coincides with, or what is it related to? Is it
The ones on the
1,
far right.
3, 3,
No.
3.
So from 1, 3, and then this point, right?
Yeah.
Nice. Is this clear to everybody?
Yes.
How do you
Looks so.
calculate? Go through the edge and then walk with the stride. That's it. So go through the edge. Here's the same edge. We walk with a stride of 2. So we start from here and compute the 3 by 3 matrix that we are interested in. Was this clear?
Yes, actually, very
Yes,
thanks.
thank you.
Ah, nice.
Actually, this exercise like makes the work like we have a close minds, but actually we have only 2 by 2 convolutions actually. And now you show this exercise, and we start thinking about like some 3D objects in the space, and actually thinking by
Nice.
our heads and not by like calculations. Thank you very much.
That's amazing. It's very important for you to imagine these things in your head because you're going to do this in the quiz right now. So the quiz time is here. Everybody's here, I hope. Mustafa Ayman, are you here?
Yes, I'm here. Thank you.
Хорошо. So I would like you guys to just, I will open the quiz. I'm not sure if the quiz is correctly done, so please check it out. This is the first time I make a quiz on Moodle. So if there are any bugs in there, so just forgive me, guys, okay? I will make the quiz unhidden.
My question.
Yes.
Could you again explain about max pool?
Max pooling on where?
I don't know exactly how we obtain every element in the output.
Хорошо.
In example for one element in output.
There we go. Let's share the screen again. Yeah. Can you guys see this?
Yes, we can.
Yes.
Nice. Can you please do this example for me? What are
Okay.
Yes, what are the 2 by 2 points that we will use for this value?
Okay, maximum value here is 7.
Yes, it's the maximum of which values?
What?
Tell me the values that it's the maximum of. So for example, if it's the maximum of 7, 3, 3, and 9, or nice, that's great. How can you guys draw on my whoa? I didn't know that you guys can draw on it.
Artificial intelligence.
My brain just like exploded. Great. So this is Maxime doing it. Can you tell us how to do this, Maxime, so that Sasha also does it?
Yes, and instead it.
How do we clean this, Maxime?
Go to annotate and
Oh, genius, Maxime. Bro.
Just raise.
Aha. Go ahead, Sasha. Can you do the same thing that Maxime just did and surprise us?
Hello, Imad.
Oh, no, I don't know how to do it.
Nobody does, I think.
It's in view options and annotate.
options. Okay.
At the top of screen.
Ah, okay. And draw, yes, something like this.
Yes.
Так.
Hello.
Okay.
So for these, for this 7, can you show me what group of points are we using for this
In
7?
the how to say?
For 2 by 2 kernel.
I can't show. It's doesn't draw.
Doesn't bother. Let me draw for you. Okay, I will be drawing. Is it these 3? Is it these 4?
No, no.
Is
It's
it
for
these guys?
just, yes, yes, square.
Хорошо. If I wanted to make a what is it called? A 3 by 3 kernel. Can you
It's
tell
3
me
by
this?
3?
Yes, it's a 3 by
Will be
3.
9. Will be 9.
Perfect, nice. Then you got the idea. Now let's go. Can somebody clean these?
It's not mine.
Who did this?
Maybe you need to press. Like,
I guess I did, but I don't know how to clean. Where is?
Okay, disable annotation for others. Yes, I can do it. But now since I disabled it, you probably guys cannot clean it, huh? Wow.
No, you
with-
definitely will not be able to clean it because you disable ability to clean it.
We're
in my-
stuck.
You can clear all drawings instead of clearing your. Like,
Where is it though?
Hello.
Hide floating.
the
menu.
third last or second last. It is like second last before save. There is clear.
I think you guys can see something different than I do.
I will send a photo.
Definitely, we have it.
Ah,
in
nice.
Confuse.
Found it. I see that Zuhair Abbas is trying to play around, so next time you're gonna be kicked out. So the same person who just struggled a little bit with the first one, can you tell me what would be the output of a 2 by 2 max pooling filter for this point?
With which stride?
With the no, it's just no stride. For now, we're just using one value.
2 by 2 by 2, you mean?
Yes, for this one, for 2 by 2.
It will be 7.
Sasha, I mean, I'm speaking. Yes.
Ah, sorry.
That's
Sorry,
okay.
but I don't understand how we obtain 9 in this case.
It's wrong.
For
It's
3D.
not 9. It's not 9. So basically, this is what we're saying. There is an error in this calculation.
Ah, error.
Oh,
Oh,
yes.
okay. And why is it 7?
It becomes
Because-
7, right?
Yes, from first
Right.
square we obtain 7.
Can you tell me what this square should give? It's also wrong.
Okay.
So this square corresponds to which
4?
area?
No. Sorry, I don't understand how you get.
Exactly. So let's do it together here. For that square, for this last square in here, for 2 by 2 kernel with stride of 2, these are the values that will be taken into consideration. What we do, we take the maximum of these 8 values. What is the maximum of these 8 values?
Oh, yes, 6.
Nice. So for this case, it's 6. Can you tell me what are the values for this one?
So here will be 4, yes?
Perfect, perfect. Then you have just understood everything, right?
Oh, I
You get
understood.
it? Nice.
Thank you.
got it. So
But I guess we already explained this one. If you miss it, just record a lecture, record it. I mean, just wasting time, I guess. If if we might explain multiple times.
it's very important for everybody to understand because the quiz will be about these.
Yeah, because you explained before, I assumed, and this is the second time when you try to explain.
Sorry.
etc.
Yeah,
Oh.
just yes, try to listen lecture after that. Actually,
that's
I'm not
okay.
agree.
Now let's start with the quiz. I will give you guys, well, I will give you 10 minutes, and then I will see if you guys finish in 10 minutes or not. Okay?
And if we are not, you will extend.
I will extend with 5 more minutes, but
Okay.
no, I have no idea what's happening right now. I don't see the questions. Edit settings.
does listeners possible to take quiz or?
Yeah,
we
you
just-
can help me out, Anton, if you are a listener.
Yeah, I have the
Yeah, I
same
think
question.
the listeners also can take the quiz if they want, but they will not be graded. So that's, yeah.
I see.
So it's
Oh,
9 April.
how we can take? I see quiz requirements only. Where is quiz here for listeners?
Check the
one
recording.
second. Let me try to finish this one here, right? And I believe now you can see the quiz.
You are right.
Yep. Thank you.
Can you guys see the quiz? Can free listeners also see the quiz?
No.
That's you.
Yes, sure.
You guys can see it.
Yes, absolutely.
That's nice then.
Can we start?
Yeah, go ahead. Start, guys. Start. And go fast because the quiz closes at 17:50.
I guess again, listeners cannot put continue. If you put continue, we go to the main page of the course. So sad. Yeah, we go in, but we cannot type continue.
That's good.
So sad, right?
I think we can do what is it called? Right. Put in waiting room. What are they called? Like those separate rooms? This technology is killing me. Okay. How do we create breakout rooms?
It goes, we need to enroll in this course before you can attempt this quiz. Yeah, this is kind of.
Well, that's okay. That's okay. We will do the quiz right after you guys finish the quiz. We will go through it and show the answers. So no
Sure,
problem.
thank you.
Hmm? No cheating.
I have a question about fifth question.
And the third and the ninth.
Yeah, a polling layer with the same stride, kernel size, and padding. What do you mean same stride, kernel size, and padding? It's
So
not clear.
no. Continue the sentence. You will see same as what?
Yeah, same as what?
As
That's
a
a question.
convolutional filter.
At what?
As a convolutional filter.
Yeah, so if you say you have the same stride, kernel size, and padding. So for example, you have stride of 3, kernel size of 3, and padding of 3.
Oh, no,
Yes, exactly.
Yes. So basically, you have a max pooling layer, a max pooling operation, and a convolutional operation. They both have the same kernel sizes. So, for example, 3 by 3, stride one, padding.
You mean the operation of pooling and the operation of convolution with the same sizes, yeah?
Yes.
Nice.
Convolutional operation and a max pooling operation have both the same sizes of these parameters, which are the kernel size, padding, and stride. Do they have the same output size or a different output size? Because they are different operations.
No, it's clear. Thank you.
Nice.
Can we also please discuss the third question? Like 10 layer without activation between them and 1 layer. So 1 layer means there is an activation.
Just
yes, actually.
without activations.
Yeah, so 10 layers without activations and 1 layer with activation, they're not the same, right?
I see that some guys are sharing the solutions in the chat, and that's what.
Let's done them.
So Imad, about the third question, 10 layer network without activations between layers is equivalent to 1 layer neural network. So can we say if this 1 layer is with nonlinearity at the end and 10 layers without nonlinearities, that they are not the same? Huh?
Both of them without any activation functions.
Aha.
At the end.
Mm-hmm.
Okay, so if they are all without, okay. And the ninth one, GradCam is just a weighted sum. And the GradCam on the diagram, we had ReLU. So it is weighted sum plus ReLU.
And what?
ReLU, rectified linear
function.
unit. Yes. So GradCam is not just weighted sum, it is a weighted sum and ReLU.
Should we think that you suppose that it's a weighted sum plus ReLU or not?
Yes, that's a better, yes, that's, I just wanted to make it simpler. So let's consider it, yes, weighted sum plus ReLU.
Okay.
Matt.
Yes.
Actually, I finished the quiz. Maybe at the end discuss some answers actually and questions because
everybody finishes the quiz, we will go through the answer.
Yeah. Okay. If you cannot go through the question 6, just input 1 single number in the question 6. This is not like
I gave it 1 single number, it's not going ahead.
It's 1 single number because it's asking about the width of the output.
In question, I cannot go to question number 7. There is some problem with Moodle.
Can you refresh?
Let me try. Yeah, it worked.
I think 5 minutes are left now.
I have a question.
Yes.
In the question of GradCam provides heat maps for, there's like an answer, it doesn't care about the output. What does it mean it doesn't care about the output?
I think the answer is pretty clear. Just go to the slides. The first slide that speaks about GradCam will give you this answer in a short. Yes, again, this is a open book quiz, so basically you can access the slides whenever you want.
Ah, okay.
Just a hint, sometimes TAs put some random answers just to feel the body of the question.
Exactly. So just basically just something that doesn't really make sense, just to bluff you guys to, well, is he doing something completely random or is he at least thinking? Anton, we will do it. We will do them together very soon. Don't worry.
Okay.
The thing that's concerning me is that there are 40 students that should be enrolled, but only 23 are taking the quiz. Ah, it's the free listeners, right? Yeah. Sure.
Listeners who already left us.
They just wasted.
8 seconds, 6 seconds, 5, 4.
3, 2, 1. We are ready to start. Go.
Ignition, lift off.
Nice. Хорошо.
Show us distribution of marks.
Nice quiz.
It's very easy. So this is the first quiz. I made it supremely easy for you guys. I'm just gonna do something because somebody just scared me in the chat. I'll just confirm. I don't know. Kind of sounds logical so far. Let's see the results. How do I see the results? Results, right? I see. Nice, nice. So far I see a lot of 9, a lot of 10, a 7, a 6. Okay. Nice. Let me show you guys the distribution of the results. So this is the distribution of the results. So a lot of people are in this area, some people are in this area, but that's good, right? Let's go through the quiz and solve the questions together, right? Tick, tick. There's the quiz. So first one, perceptron is similar to base models, decision trees, or logistic regression. We just said it in the revision. It's similar to logistic regression. Activation functions are used only at the end of the neural networks, which is not correct. It's used also in the middle of neural networks, right? After each layer. 10-layer neural network without activation between the layers is equivalent to a 1 layer neural network. It's true because if you don't have the activations in the middle, then every two consecutive neural networks are just the same, then you guys can just do the, what is it called? The proof of recursive proof.
Can we please try to avoid in the next quiz such ambiguities when what you exactly mean without activations, either just the 10-layer network or all of them?
Okay, let's, from the next quiz, things are going to be a bit more difficult. So I think they're gonna be a bit more clear, right?
Thank you.
To reduce overfitting in neural networks, we can reduce the size of the model. Is this correct or not?
Yes, it's correct.
Nice, that's a good question. That's a good answer. A pooling layer with the same stride kernel size padding of a convolutional layer provide the same output sizes. Is this correct?
Yes, because formula is same.
Exactly. So the formulas are the same. If these values are the same for both of them, then the result will be the same. Can somebody tell me what is the output for this one?
89.
No, it's 7.
7.
Let's put it to the formula, guys, right? So let's write, annotate text. If we have 7 plus
2
minus what? 3. How much is this?
6.
Yes. 6 divided by 1. It's 6.
It's very hard to calculate.
6 plus 1.
7.
Oh, great, guys. You guys make me proud. So basically, this answer is 7. I can't answer here. Lime interprets which model? Does it interpret the original model or a simple model trained by Lime, by Lime process itself on the same training data, or is it a simple model trained on a randomly sampled data, right?
Actually, I have a objection about this question.
Random data based on something we want to evaluate.
So which one?
Last one, C.
C, exactly. Can somebody tell me why C and why it's not B? So basically, of course, everybody knows it's not A. So because we're interpreting the locally made model, right? But why is it not B?
Because we do not use like web data from original model, original data set, because actually it is in not like all the data sets, it is in the one exact sample, and want to take maximum information about this sample and about this neighborhood.
Exactly. So basically, if Lime did the same thing that we're just saying, if Lime requires the training data to operate, then that makes it completely infeasible to use, right? So basically, we want to use Lime at the inference time, right? To understand or interpret the inference. If we still need the whole training data for inference, that means the method is completely useless. That's why Lime, what he does, it doesn't just use the training data, but he uses a synthetically generated data by either if it's tabular data, then he will just put random everywhere. And if it's not tabular data, for example, it's text, he will just try to remove some words, keep the words or remove them and just generate different samples.
May I ask a question? Like with some question, it was referring to the 5 points, how we can interpret the model. Like first of the model, the training itself, and like, like 5 options. Like the last one was like one local answer, when some local answers, and actually like in general, two in general, and then like a training itself. Like it was referring to this information. Yes.
Mm-hmm.
Okay.
Do you guys have any other questions also?
No.
No.
Nice. GradCam provides heat maps for
each class separately.
Exactly. So for each, sorry, I will just close this. GradCam provides heat maps for all classes together, each class, or it doesn't care about the output, only shows the important parts of the image. So basically this was just here to fill in the gap and just see if somebody does not understand completely or he's just clicking randomly.
What
Uh,
confused me in this question was like the important parts. I know that each class separately, but it shows also the important parts about why the model like classified this object as it is. So it was.
the thing is, so this one, it's not completely random. Let me show you the lecture again. And no, because we gotta go to the next lecture. So just basically, this one, the one that I just described here, is a completely other model for image interpretation. So it just shows you what are the important parts of the image, right? But GradCam does not focus on all the classes together.
Yes, it focuses on
Only
each class
one
separately.
class at a time. Now, Nat, so GradCam is just a weighted sum of the feature maps. True. So basically, it's just weighted sum of the feature maps, and then if some
Plus activation function.
yes, with an activation function of RealView. So that's yeah, pretty easy. Lime can be used on images, text, all of them, or tabular data.
All of them.
All of them. So basically, if you just assisted through the lecture, you would be able to answer at least most of these questions, right? If you guys don't have any other questions, let's jump to the next lecture. Or should we take a small break?
No, let's continue.
I vote for break, 2 minutes break.
Let's take a few minutes break, right? Just refresh, hit yourself with some cold water, and let's go back.
And when we will finish at 20:30. I mean, like 8:30.
Yeah.
I mean, we have 2 classes, right? Between the classes, usually the break.
We can take break whenever we want, actually. When do you guys want break? We can take as many breaks as you want, also. I am pro breaks.
So now, how long do we have? Like 5 minutes? 10 minutes?
Let's take 3 minutes, right? Let's take 3 minutes. I'll go just wash my head with some cold water and come back.
Okay, in 3 minutes. See you.
See you guys. Enjoy you.
Hello again.
Привет.
Ну или так.
Как дела? I hope everybody's here. Everybody's back.
Yes, probably. Nikita just hiding, I think.
Yeah, I think Nikita is hiding. Should we make a rule to open the video for quizzes?
What?
To open your video cam for quizzes. When you are taking the quiz, you should have your cam open.
I don't like this idea.
Yeah, because you probably all are in the bed and eating some stuff, right? Or in the kitchen.
No, actually, I can. I'm not cheating, but there is a daughter and she's sleeping, and there is a very dark in the room, so
That's
I
cool.
can, but
That's okay. That's okay.
Wow,
And actually, I see no reasons to this because actually we are close to the end of this like education. Actually, I see no reason to cheat at all because I want to learn, and I think most of us want to learn, but not like.
Exactly. So you guys don't have to worry about the grades. I will make sure that all of you guys get at least a good grade. So this is just an elective course. So usually elective courses, everybody gets an A or a B. So that's not a problem. The goal of this course is just to give you something that will help you quickly get on your feet and get started in either a job or a research position at Innopolis University or somewhere else, you guys. So basically having some experience with the models we will be working with is very important. So the same thing for classification. If you can get in with a company and quickly in the first week, you already gave them some results, you already trained some models, they already see it, that will help you stay with that company a little bit for much longer, and that will give you a bit more respect in that company, you know? So it's very important for you guys to have at least like a starting point for a variety of different examples, for image classification, for object detection, at least something you can easily do in a matter of day or a week, and get the results showing for your company or your supervisors.
Naturally, thank you
Matt,
for quiz.
can we like have some time, maybe like, or maybe it will be like advanced lecture for natural language processing,
on NLP?
Or somehow combine it with computer vision?
Yeah, I mean, we can do something with NLP and computer vision, like image capturing and these things. Yeah, we can easily do these things. Like in the end of the course, we can have as many optional lectures as you guys want. I mean, I'm available all the time.
Thanks.
And actually, Imad, thank you for quiz because actually vocations were like really qualitative, and actually like I also made the mistakes, but actually after your explanation of this quiz, I actually get to a point where I was mistaken. It was like really help to make my knowledge about this lecture stronger. Actually, I think actually I think you from my point of view, you need to like to follow this like concept of creating quizzes and actually of rechecking quizzes after them. I think it's really helpful. Thank you very much.
Thank you for the feedback. That's very important for me, I think, this kind of feedback. So if you guys have any type of feedback on the method of teaching, these things, you can always feel free to share them either during the lecture or preferably after the lecture. Send me just a message on Telegram, right? So the second part of today's lecture is about object detection. Let's go. So during today's lecture, we will be speaking about object detection and RCNNs. Fast and faster RCNN, and we probably will not go into YOLO and Detectron. So basically this part will be done in tomorrow's lecture, where we will be speaking in more depth about ROI pooling and all of these different architectures. We will speak about them in a bit more depth for tomorrow, right? So today we'll speak about the architectures in general, not model specific, such as YOLO v4, YOLO v3, or Detectron. We will speak about the architectures in general. Tomorrow we will go in more depth with these types of models. The first part will speak about object detection and RCNN. So basically the R stands for region-based convolutional neural networks. We will speak about what is object detection, what's the expected output of an object detection model. Just give some examples of applications that you guys can create for your final project. and basically what is the basic first model for object detection that we can easily create with the knowledge that we have right now. And then we will get into more details about what is RCNN and how is it trained, its loss functions, and right? Object detection. So the first, let's say, comparison or first difference between an object detection and a classifier. So the classifier attributes a tag or a label to the whole image, right? So for example, here there is a cute cat, but we have no idea where is the cute cat located inside the image, right? Whereas for object detection, we have multiple objects inside the image, and we try to classify and detect the location of each one of those. Can somebody tell me? So this is for classification. How do we create this box, right? This is a rectangle. Mathematically, how can you define a rectangle?
Center and height.
Nice. So basically the center point.
Or usually just 3 points around the rectangle.
Can you repeat?
3 points or 3 corners of this rectangle.
3 corners. Can we do a bit less than 3?
2 points.
Yes,
I can do it with
top
2.
left and bottom right.
I can do it with 1.
Wow. So basically one way to do it would be a central point and height and width, or providing the coordinates of the left upmost pixel and the right this point. So basically the one that is in the bottom and the right. Another way to do this would be with this point and the height and width, right? So there are different ways to formulate the location of the bounding box, and this difference is gonna you're gonna spend a lot of time worrying about this difference, because in most cases you're gonna be working with different models. Each one of them will output a different format, and if the code is not well documented or well commented, then you're probably gonna be lost on which format is being used in here.
It's all code we have, yes?
Yep. Now, vehicle counting. This is the first example that we will do. So it's a combination of object tracking and object detection. Let's watch this video together. You see? In, out.
Wow, very big track.
Yeah. This is the road from Innopolis to Kazan, right? There you go.
Russian United States, right?
But this is very important, so you guys can see. First thing, what it's doing is, let's go back here. So first thing, it's detecting the objects in each image separately. So for example, this is car 1, car 2, car 3, car 5. Yeah. And between the different frames, so basically the first one was an image. We sent it through our model. The model made its predictions. Now this is the second image. We sent it to the model and we made its predictions. But what you can see here is car 73. This number or this tag follows the car on all of the road. So basically we are tracking this object in the different, what are they called? Different, these. In the different images of the video. So this is what's called object tracking. So basically we track an object inside the video, even though our model only predicts on each image separately. With object tracking, we can still make this link between all the images and how the object is moving within the images. And then what we did here was just simply make a line, and every time the object or the center of the object crosses this line, we count, we increase the counter here, or we increase the counter here. This is a very important or very good example of something that you guys can easily do. So it doesn't really require you to train a new dataset or train a new model. There are already enormous amount of models which are already able to track or to detect cars and trucks, for example, all you will have to do is add, for example, a simple tracking algorithm. We will speak about tracking algorithms later on, such as sort. And there you go, you have your vehicle detector, or for example, a people counter or something like that, right? So this is something that you guys can easily do for your final project. Keep this in mind, it's a good example. Another example where we can use object detection is facial detection and recognition. So basically we combine object detection to detect the bounding blocks of the face with facial recognition. So there are different techniques to do facial recognition. The most trivial one, or the direct one, would be to embed the face of a person in the training, embed the face of a person in inference, and then you just make the distance between them. If the distance is higher than a certain threshold, then it's not the same person. I think that most of you guys already know how to train a facial recognition neural network. Did you guys already do this?
Yes.
Nice. So this is for the second year's data scientists. For the others,
I did it, but it wasn't successful.
I didn't.
I did using guns. So it was really funny to train guns.
I use some library of Python.
Nice. So basically the neural network types is very simple. What we do is we take an image, of Imad, for example, in here. We take another image of Imad in another place. And what we do is embed them and try to bring them closer, right? We try to bring the faces of Imad, the embeddings of the faces of Imad together, clustered together. And we take, for example, the face of, let's say, Nikita, embed the face of Nikita, and try to bring or to make some distance between the embedding of face of Nikita and the embedding of face of Imad. So basically, we'll have some small clusters of faces of Imad. These are the embeddings of face of Nikita. These are the embeddings of face of Anton and stuff like this. And when you have the inference, you just put the new image, check the embedding. If the embedding is in the area of the face of Imad, then he's Imad. If it's in the area of face of Anton, it's Anton. If it's in the area of Nikita, then it's Nikita. This is a simple abstraction of how things are done. You guys can improve this further by, I'm sure the masters already know, by using graphs to just do this comparison of the latent space, just to speed it up, because if you have lots of people and a big training data, you're not going to have to compare one by one, so you're going to have to use some different techniques to speed up this process. This is also a very good example for an application you guys can do for your final project. It's very simple. Probably the code already exists out there. What you have to do is just like use it and improve it by adding the things that I just said with graphs and comparing the faces using graphs, right?
Actually, may I make a small note about the physical edition? Actually, during the summer internship, we also have a case from a company where we had an office in Kazan, and actually we had many videos of just recordings of this from the office, and actually were many images of all the employees of this company, and actually it's was a real case, and it's still a good case for working, it's still in use, and we still a lot of work to do.
Yeah, of course. And that's a great example. So basically, this kind of projects will definitely help you later on in your industry. I'm not sure if it's going to help you guys for research, but it's good for industry, right? For people who go to the industry.
Can I ask about the face recognition? Have you ever seen the approaches? How can you combine face recognition with the data from the LiDAR of the phone?
With the LiDAR of sensor fusion?
I mean, here in this phone, you have a LiDAR that scans the face.
Yes.
So you can also have the depth map and the RGB.
Yes.
Maybe you can combine somehow the depth map with RGB, and then train them not on the 2x2, not on height by width by channel, but height by width by channel by depth.
Yes, that's.
Will it be any different?
It's definitely going to be more accurate. So, for example, the laptop that is right next to me right here, uses 3 different sensors for the depth, just to recognize my face, along with of course, the camera. So definitely this is going to be very useful, and it definitely helps. How do they do that? Not really sure, because I haven't worked before using what I call the depth maps and LiDAR data. I haven't worked with these, but if you guys want, I could check if there are some public data sets that use such data or such formats, and we can build some models on them. Yep.
Actually, I may say what even find the like many good pictures of the one exact person, like for just training facial recognition, and in many persons is really hard, because like it's sensitive data.
Exactly.
And about the leader, I really questionable about it, because it's really biometrical data.
Exactly.
Under the highest protection level.
Yeah, but from iOS 12, you can access the data of the LiDAR on the front side.
No, for you, not for other people. Let me say.
Yes, for other people, it's
no. I mean, you can create an application and use your friends to gather the data set, and I think it may be even publishable.
Yeah, that could be a great idea. We can discuss this a bit later on after we finish the lecture. We will have like a 30 minutes talk, and we can discuss these ideas. This is a very good idea, actually. I really like it. Another example, which will be the example that we will do in this in the lab right after the lecture, which is parking lot monitoring. So basically, you try to detect the free spaces inside the parking lot by detecting where the cars are and where the cars are not, right? This is just object detection, completely simple, and the data sets for these examples exist everywhere, so they're all publicly accessible. I'll just check the chat if somebody asked something.
There is nothing useful in the chat.
I see. Oh, yes. So the first model that you can already train yourselves for object detection is the sliding 2D CNN, right? So we just basically take a 2D CNN model and we slide it through different parts of the neural of the image. Whenever the image just spikes or activates, we will decide that this is the location of the object. So it's a very simple model, right? Can you guys already understand how this model works, or what are the problems in this model?
Problems if like we have the object what we want to detect is bigger or smaller than our like square.
Or too many objects in square, maybe make it adjustable.
Let's see.
It's possible to, I mean, if it's finding too big object, it's increasing like amount of squares to cover this object. Or if it's a lot of small objects, it's separating
But if you're,
big square.
Yes.
But you cannot have the frame bigger than the picture, and the object can be very close. Like you cannot tell that this is a pen.
What if we have
Like
a
you
lot
can.
of objects also? It will
That's all of these points are very good. The first point that I wanted to speak about is the amount of computations that you will be making. So since you will be sending this image to the model, sending this image to the model, this image to the model, and this image to the model, you'll be making a lot of convolutional operations on the, so basically you will send many classification operations for just one image. And this takes a lot of time and a lot of computations, right? Another problem would be the stride, right? So basically, do we just cover this one and skip all of these and go to the next one, or we walk pixel by pixel and get some overlapping images, right? So the overlapping idea gives you a lot more accuracy, but at the same time, it's expensive. It's an expensive operation.
If you will do it pixel by pixel, track will go on.
Exactly. So basically, it's going to be very hard. But what we can do is make the image smaller. So basically, downsample the image, right? And then pass it through our detector. And only the areas which were highlighted or which were interesting inside the small size will be searched inside in the bigger size, right? So basically, we send it through this small image, and it will highlight that this area is important. We go make it bigger, and then we slide it, find the area inside which is important, make it bigger, find the area which is important, make it bigger, find the area which is important. This will give you a bit much better or better results, but it will still be a little bit computationally expensive, right? Another solution would be to use something called a selective search. So basically, instead of using the neural network or CNN on every single patch of the image, we can use some machine learning algorithm or some like predefined algorithm, which will search for interesting areas. So basically, let's say this area was very interesting because it has a lot of pixel differences and stuff like this, right? But if we look at this area, the pixels are not changing that much. So we would say that this is kind of background, it's useless. So this kind of algorithms can be used to propose regions of interest where the CNN can be applied, right? So basically, instead of just blindly applying it everywhere, we will be applying it only on the locations which interest us, right? So this is selective search.
This method is based on what kind of network, neural network?
This is just basically basic CNN, right? So just the convolutional layers followed by some max pooling layers, followed by fully connected layers and classification in the end, right? So basically, this is the basic model that you can have. It's a 2D CNN model, very easy for classification. We slide it through the images. This
I think the question was like how we going for this image by the square. If the square sometimes highlight and sometimes not highlighting.
No, it was not answered my question.
Okay.
Nice. Okay, so the question was answered before?
Yes, you answered it.
Хорошо. Now, before we continue and speak about the improvement of this model, let's speak about a concept called intersection over union. We will speak about something else called a slice dice loss tomorrow, but now we will speak about intersection over union just as a metric of evaluating how good a bounding box is, right? This is equivalent of accuracy for object for classification, remember? So in order to evaluate how good a model is for classification, we use accuracy. But if we want to evaluate it for object detection, we use intersection over union.
It's like popular metric.
Yes, let's imagine different scenarios for this image, right? I would propose this box, right, where we have the whole image inside the box. Is this correct?
One more time, please.
Let me annotate it, right? Yes. So I propose, sorry. Why I cannot draw? There you go. So I proposed this is the bounding box that the model gave. Is this a good bounding box?
No.
For one object,
Pretty
right?
well.
So it does contain the box, so that's good, but it's not very strict on the box, right? So it's very loose, and that's bad. Let's imagine a different scenario, right? This box. This horrible box, right?
Horrible.
Horrible.
If it's not for sky classification.
What about this box?
It's not zero.
Better than the previous two.
Good.
It's
we
better
can
than the previous two.
We can refocus using this box, right?
This is what intersection over union actually calculates, right? So it basically takes the bounding box that we propose and the original bounding box, or the ground truth bounding box, and it computes their intersection over their union. The higher their intersection is, the better, right? So if these two predictions or the prediction and the ground truth overlap a lot, this means it's a good thing, right? This is the intersection. If their union is bigger than their intersection, that means it's a bad thing. So for example, the first case where we spoke, the example here, for example, yeah. So in this case, the union is very big, right? So basically this plus this. So it's a very big number and their intersection is very small. Same thing, same thing, same thing. In this case, their intersection is okay, right? So basically this is their intersection and they still have some points in their union which are not covered. And these points will be used to what? Will be used to penalize the value of IoT. So basically the IOU to make it smaller. So to say that it's not perfect, right? So if the intersection equals the union, that means it's a perfect example. So this one gives you 1. If it's anything less than 1, then it's not as good. If it's 0, then the intersection is 0 and the union is very big. And this means the box was completely outside of the area, right?
It's linearly evaluated, right?
Can you repeat?
It's evaluated linearly, or I mean, like 90% box and 50% box. It's equal to 90% of intersection and 50% intersection, or maybe every consequent pixel that inside box is matter more.
I didn't get the question, but let me describe it again. So for example, here we have 500 pixels. We use 500 in this area, right? In the intersection, we put 500. In the union, for example, we have 700. So basically it will be 500 pixels divided by 700 pixels, and that would give you 0 point something, 0.8 or 0.9. Right?
Okay, I understand. That's enough.
The second concept that we should cover before going forward is non-maximum suppression. Remember the example that we just spoke about where we are sliding the CNN in this area of interest. So for example, we decided that this is the area of interest. We keep on sliding the CNN in different parts, and it will give us these different rectangles, right? So these are different activations for the same object. How can we erase the different predictions for the same object? How can we keep just one for each object? How would you imagine this scenario?
You mean how we make one? We just compare scores, right?
Yes, we can compare their prediction score. So for example, this one gave me a prediction score of 0.6. This one was 0.7. The one in the middle gave me the probability, the output probability of the CNN was very high. So the CNN was very confident in its decision, and it said 0.9, right? So I decide to keep only the 0.9. So this is one idea. The small problem in this idea is how, so for example, if there was another truck in here, and the other box was detecting the other truck, how can I keep 2 of them instead of keeping just 1?
We can use the intersection of reunion between the 2 boxes.
Between each box, right? In the prediction, we use the intersection over union between the different boxes to decide, is it the same object or not? So between this box and the consecutive box, the intersection over union is high. That means we are speaking about the same object. We can remove one of them. But if we had an object in here, that means these boxes are not for the same object, and we should not be comparing which one should we keep. Right?
Yes.
So basically, this is the non-maximum suppression algorithm. The steps are very logical. So basically, we just created the steps together. We select the proposal with the highest confidence score. remove it from B. B is the list of the predictions that we have, all of them, and we add it to D. D is the final list, which will have the only the maximum predictions, right? Initially, it was empty. So basically, at the start, it only has one, the supremely most confident prediction or most confident box. And then we compare that box to all the values in B. If there is a high intersection over union with that confident box, we delete all of them. These highly intersected boxes, we delete them. And again, we take the proposal with the highest confidence that is remaining inside B, remove it from B, compare it with all the values that are in B, find anything that has a high intersection over union with this new box, remove it, and then continue iteratively again and again and again until we have only boxes with high confidence and they don't overlap with each other. And ta-da! This is the first part of how do we build this simple model of basic sliding CNN. So basically we slide the CNN, we can improve it a little bit for speed by selecting the areas that we're interested in, or we can use a different algorithm, which is manually searching. And then we can just calculate the intersection over union of the different predictions and keep only the maximum boxes or the boxes with the highest confidence that don't interact that don't intersect with the other boxes. Now that we have this cleared out, let's speak about the first architecture of the day, which is RCNN. So RCNN is let's say, kind of the same idea that we just described, but it's more technical, right? So basically, the first step is we take the input image and we try to extract the regions which interest us. So basically, RCNN uses this algorithm. So it uses some machine learning model that just looks at the image and says that this area sounds interesting. This area looks like it's useful, right? So basically, it proposes the different areas for us. And then these areas, each one of them will be wrapped. So basically wrapped, let's think of it as resizing, right? So the algorithm that we will use might take 100 by 20 pixels. Another place would be 50 by 50. Another place would be 60 by 12. So basically we resize all of them to fit in this the same input size. And then we feed it through a simple CNN, right? So basically this part is what we were just speaking about, which is the sliding model. Just CNN layers followed by some fully connected layers, and then you classify yes or not. Very simple, right?
Do we take 2000 regions for each image?
Yes. So basically the algorithm used in here is, as we said, so it's an algorithm that just looks at the pixels, says that this kinds of interesting region, yes or not. The algorithm proposes around 2000 interesting regions inside the image. Again, 2000, of course, is much smaller than going through the image pixel by pixel by pixel by pixel and seeing all the combinations. So it's definitely an improvement, but still 2000 times running a CNN is a lot. So selective search, just so we can get one idea of what a selective search algorithm might look like. Generate initial subsegmentations. So basically we generate a lot of candidate regions, and then using a greedy algorithm, we try to combine these, what are they called? These regions together, just to reduce the size of, or the number of, what are they called? The number of proposed regions. And then we just continue iteratively training and training and training until we satisfy some criteria, and then call it like an end and say these are the regions that we decided to keep. It's a very simple algorithm. I wouldn't really go into how much or into details on how do you combine the similar regions, how do you define similarity between regions. So just basically a computation between the values of the pixels. If the pixels are similar to each other, we bake them, right? So this is not really something that really should interest you, but it's something that has been done. Old, nobody uses this anymore, but it's useful to understand. Some problems with the region-based convolutional neural networks are the following. Training time is humongous. So basically 2000 classifications for one image. Inference time is is also horrible. So basically inference time is around 47 seconds on a good GPU. And selective search is not something that is dataset specific, right? So basically the proposed regions are not something that you're going to be learning from the data. So this is something that's going to be algorithm specific. It's going to be used for medical images where you're looking at MRI scans. It's going to be used for paintings. It's going to be used for photos of cars, photos of dogs, for everything, right? And this is something that is not good. So there is no such thing as an algorithm or a heuristic that works for all different types of data sets very well. So this is a very cool example where this point is the biggest problem in this algorithm, right? The output of the model is the following. So basically, after we finish the convnet on each rectangle, you see the sizes of the rectangles may be different on the image, but once we send them through the convnet, this is the same modeler, we must resize them all to fit the same shape. And then we send them through the same layer, so this is the same neural network. We send them through this neural network, we get an embedding, and then we use SVMs for classification. And this part, which is called B-box regression. Can somebody tell me what B-box regression might look like, right? So bounding box regression. What are the output of bounding box regression? What is the output of a bounding box regressor?
Maybe the probability that the bounding box will be here.
Remember when we just said here, how do we define a bounding box?
Maybe the regressor will provide you the X and Y components of the center of the box, or 4 numbers like the top left and bottom right corners.
Perfect. So basically the bounding box regressor would be giving you the coordinates of whatever situation or whatever format you want to use. So let's say we want to use the top leftmost point and the bottom rightmost point. This is how we formulate a B-box. B-box regression would be giving you the coordinates of this point and the coordinates of this point. So let's say this point is 50, let's say 350, 50, and here it's 450 and 700, right? So this is what bounding box regression gives you. This is what bounding box regression gives you. So this convolutional neural network is going to be trained for classification and for regression, right? For classification, what kind of losses do you usually use for classification?
Cross entropy.
And what kind of losses do you use for regression?
Mean square error.
MSE.
Exactly. So basically, you can train this model using mean squared error and help me out, guys.
Cross entropy.
And cross entropy, depending on whether you want to be doing binary classification or multi-label classification, right? Now let's take a small point and try to propose areas of improvement on this model.
Can I ask a question before you continue?
Yeah, of course. Yeah, go ahead.
Can you give a concrete example of how can we do the first step, proposing 2K regions? Yes, from 1 to 2. Can you give like some examples of how can we do this?
Well, let's remember superpixels that we just saw in the previous lecture.
Oh, yes.
Well, we can consider that these superpixels are regions of interest.
Okay, got it. Thank you.
So basically, the superpixeling algorithm, which is just a simple algorithm that just combines or clusters different pixels together based on their location and their color. We just continue combining, and then we stop at a certain criteria. So if you are already familiar with what is it called? Hierarchical clustering. So you can imagine this one as a hierarchical clustering algorithm, but that focuses only on the neighborhood of the pixel. So basically, if this pixel is close to this other one and looks the same, we group them together. We keep on repeating this algorithm multiple times, and there you go. You have multiple regions.
Okay,
again, something that is a bit different on this clustering algorithm, a pixel can belong to multiple regions, right? So you can see here that these pixels belong to this region, and they also belong to this region. So that's not a big problem, right?
Yes, got it.
Nice. This selective search algorithm is not really going to be very important for you in your future career, but I will give you some some links and some resources just to see how this model works in real life, right? Work in real life. The second step is fast RCNN. So the first model was called RCNN, and the same researchers decided that their idea was very bad or was very slow. So they decided to make something called as fast RCNN, which is another paper on how to improve only the speed of the model, right? The big problem that happened inside this area was the extraction of the regions. So basically it's extracted 2,000 regions, and the algorithm itself of creating these regions was very slow. So what they decided to do, let's take the image,
remove this step,
kind of remove it, but kind of keep it, right? So they did keep the selective search algorithm, but they took it on a different step. Instead of applying the selective search on the image itself, we first send this image through a set of convolutional layers, and then we get what? A convolutional map. Usually this convolutional map is much smaller, right? So basically the combinations would be easier, and the trained convolutional map or the convolutional map is something that is trainable for every data set, right? So basically we have a CNN in here that's going to learn a convolutional map, feature map, dependent on every data set. So it's not something that is the same, or it's not something that's going to be the same for all the data sets, for medical images and for images such as this. The feature map is going to be specific. And later on, what they will do is they will apply some other searching algorithm on this convolutional feature map, right? If this area is interesting, or if this area, for example, has high activations, then we send its corresponding image to the model, and we do the classification and bounding box regression. This is the idea in general. The improvement of the speed, so you can see this is the RCNN. Definitely the training time is much faster now because we don't have to run on 2,000 images. It's a bit less. And the second thing is let's see. This is the difference between the test time, this is the inference time, using region proposal algorithm and excluding the region proposal algorithm, right? So remember, we take this image, we create the feature map, and then we start searching in this area, in this feature map. So these are the times including and excluding the region proposal. Go to the fast RCNN. This is what's important for us. So you can see that excluding region proposal, fast RCNN is a super fast model. The only problem it's having is the region proposal algorithm. So it's a very what's it called? It's a heavy algorithm in computations and time. And the idea would be, or the best idea would be, keep this same architecture, but instead of searching inside of this feature map, let's completely do it, or let's do this whole step using only neural networks. This way, we can take it even faster and reduce the time from 2.3 up to 0.32. So basically 0.32, it's starting to approach what is called, it's starting to approach real-time processing, right? Faster RCNN is the newer proposed model that will solve the problem that we just saw. So first, it will resize and input the image through a CNN backbone, right? So basically just every CNN, before you go through the convolutional layers, you should fix your size. As we have said this, the same thing, we said it here. Doesn't matter what the patch size is, we always have to resize the input images to the same size before going for convolutional neural networks. This is the case if you want to use something after the convolutional neural networks to do stuff such as classification or bounding box regression. If you just want to use CNNs on their own, then you don't really need the resizing part. So the resizing part is just to make sure that the classifier later on will have the same size of the input, right? What we do, we get the feature map of the last layer and build a mapping between the points, right? We will see this further on in other pictures, but what we will do is, this is the image. We send it through the deep convolutional neural network. Here is the feature map. This point in the feature map correlates or corresponds to this area, right, of the image. The next pixel in the feature map would correspond to this area in the image. Sorry, let's go back. Now, now that we have done this mapping, we will take a set of anchors. These anchors are just kernels. You can think of them as kernels, or you can think of them as a sliding classifier or something like that. So we will take these anchors and move them through the corresponding parts in every pixel of the what is it called? Feature map. So for every point on the feature map, we put a set of anchors on the image and try to predict the existence of an object and its coordinates. Let's put this in images, right? So we take this image, we send it through a backbone called, for example, VGG, or we could use, for example, ResNet or anything you want. So basically anything that is pre-trained model that would give you a feature map. Here we have the different feature maps of our model. And what we will do, don't look in this area first, we will just check this area. For this point in the feature maps, we will put a set of anchors on the image. And then this set of anchors, we will try to predict whether there is an object in here. So we're not trying to predict the class of the object, huh? We're trying to predict if there is an object or not. And if there is an object, we will try to predict its, what is it called? Its regression scores, or like the bounding box regression points, right? So the location of the object inside this area of the image. Why did we say the word a variety of anchors? So for example, let's take this point A, which is in the middle of the feature map. Its corresponding point would be this place, right? What we will do is we will put a set of, for example, here, we will have 9 different anchors. Each one of these anchors will have different sizes, you see? So basically this is, let's say, 2 by 1. This is a 1 by 1, and this is a 1 by 2 size. And we do the same thing on different ratios. So this is 2 by 1, 1 by 1, and 1 by 2 for big size objects. This is 2 by 1, 1 by 1, and 1 by 2 for medium objects. And this is 2 by 1, 1 by 1, and 1 by 2 for small sized objects. So this is why we have different anchors in each place. We will take this area and try to do classification on it, right? So this is what the proposed algorithm would do. For each point in this feature map, we will put a variety of anchors. All of these anchors would be fed to a CNN for classification to find basically what anchor has the best overlap with the object correctly. And again, it will also do bounding box regression to even make the best anchor to make it even tighter. So for example, here we can see that this big blue anchor is the one that corresponds to our object the most. First, the classifier would say yes, so basically true. There is a bounding, there is an object inside this anchor. It doesn't matter what kind of object it is, it's just an object for us. And yes, yep. And then we have what is called bounding box regression to, for example, bring these coordinates a bit higher, just so they can fit the person better. So putting it all together, this is what faster RCNNs do, right? So basically we have a first image that goes through this region proposal network that we just described. So basically we have a pre-trained backbone. It gives you some feature maps. Then in this feature map, we will put different anchors. On these anchors, we will try to predict whether an object exists, and if it exists, what are the corrections needed to fit it perfectly. This is the proposal part. The second part would be the part of classification. So in this case, you can think of it as exactly the same idea, but in this case, what we will be doing, we will not be doing region proposal or looking for the regions. We will be directly taking the regions that were proposed to us by this neural network. This one is already pre-trained from here. This one is extracted, and we feed it directly to this fully connected neural network that will be doing classification and bounding box regression. In this case, the classification is not whether there is an object or there's not an object, but the classification would be the normal classification that you already know, which is like multi-label classification or binary classification, if that's the case. But why is this good? Why is this important, right? So definitely you're going to say that this part consumes a lot more time than with fast RCNN, which is true. So basically what we will be doing is we will be building or training a neural network on every single part of this, what is it called? Of this feature map. And on every single part of this feature map, we'll not just be doing one neural network, but we will be doing 9 neural network for every single anchor, right? So basically for every point, there are 9 anchors. Each one of these anchors would give you two outputs. So basically, whether there is an object or there's not an object. And if there is an object, we will be doing bounding box regression. So this is very computationally expensive. But once it's done, in inference time, we're not going to be doing it again. We're not going to be training more and more and more. So basically what we'll be doing is we will go through it, put the anchors, and then we will have here simple classification or just one neural network that will propose our, what are they called? That will propose our regions for us, right? Once the regions are proposed, we stop, we come back here, send it through the VGG again, and then only the parts which are interesting for us will be sent through the other neural network for classification. This part, for example, in here, is a very typical classification model that you guys are already familiar with. Some of the details that we just skipped are ROI pooling. We will cover these details tomorrow in the lecture. I see that we are getting a little bit late for the lab, but overall, what we just covered, right? Let's go back a little bit. Faster RCNN, what it does is it resizes the input image to fit it through the backbone, gets the feature map, and on this feature map, takes, for every point in this feature map, will go to its corresponding location on the original image, put several anchors on there. So the proposed algorithm used 9 anchors of different sizes and ratios. Each one of these anchors will be trained on classification, so binary classification, or will be trained for, what is it called? Or will be trained for bounding box regression. Why is this very good, or why is this very important? As you can see here, if we take this area, for example, and send it through a neural network, the output of it would always be the same, or would be this feature map, right? So it would be in this feature map. So basically, we're not sending the image through the CNN multiple times. We're sending the image through the CNN one time. But this final part of classification and bounding box regression, which is just fully connected neural networks, this is done for every single pixel inside the feature map 9 times. So it's a little bit computationally expensive, but it's much faster than the previous algorithm, which uses a search algorithm to search inside this feature map, right? So just to summarize the advances that have been done, first, RCNN proposed regions directly using an algorithm on the image and then sent it to a CNN for classification. Fast RCNN improved this region proposal by using first, by sending it first through a CNN and reducing the size of this search area. So basically, when we are searching inside the feature map, we don't have the same dimensions as the input, and we have more rich information, which is data specific, right? So definitely there is an improvement in accuracy and improvement in speed. Faster RCNN took this even further by removing completely the searching algorithm and making it only based on neural networks. And this was done by sending the image through a CNN and then searching inside the, what is it called? Searching inside the feature map. Yeah, and searching inside the feature map using only neural networks. So basically the search algorithm, which previously was looking, is this region important or is this region interesting, only based on the data itself, is now replaced with a neural network that looks at the pixels at this area and has, for example, the correct label of is there an object in this area or not. The decision, of course, you might be saying, how do we say that there is an object or not in this area? So based on the intersection over union, if the intersection over union is higher than 0.7, that means there is an object in this anchor, and the classification would go for 1. If there's not, then the classification would go for 0. Of course, the more the anchors, or the more anchors we have, the better the results would be, and the more expensive the computations would be.
Matt, may I ask a question, please?
Yes, of course.
I understood the RG proposals from a faster RCNN, but actually I don't get the idea about a fast RCNN. How they improve the RG proposal? May you please repeat one more time, please?
Let's go back. So this is fast RCNN, right? So the first step would be to take the image, send it through a convolutional neural network, right? And then we take the search algorithm and search inside this area of, what's it called? The convolutional feature map. So instead of using the algorithm, which combines pixels together on the image itself, we use it on the feature map. And then if we decide that this area is interesting, what we will be doing, we will take this area and we send it through our neural network. So in this case, the neural network just uses an ROI pooling layer. ROI pooling layers is just they take images of different sizes and they make them of the same size. So imagine it as just max pooling followed by a resizing, right? So basically we take the input image of any size that we want, and we only keep the maximums inside that layer, but that would give us an output of the same size. So we can take an input image of 400 by 400, reshape it to 20 by 20. The same layer can take another image of 20 by 20 and reshape it into 20 by 20. So this is what ROI pooling does. It doesn't, unlike max pooling requires the input size to be the same. ROI pooling doesn't require the input size to be the same, and it always gives you the same output, right? So this is what ROI pooling is. We will see it tomorrow in more detail with some better images. Once that is done, we send it through some fully connected neural networks for, and then for, what is it called?
Classification and body box regression.
Yes.
I didn't get how, what is kind of search algorithm works in convolution feature map at the beginning. What is kind of algorithm and what does it exactly done in this feature map?
Honestly, I have never really looked deeper inside what algorithm
Okay, I
is
get it.
for searching inside the images. I will check it out for today, and probably I will add it for tomorrow's lecture. Since there is a question also on how do we extract regions from the image directly, I will also include some examples of an algorithm that is being used for extracting regions from the image directly, or the algorithm itself that is being used in RCNNs, right?
Okay, it's very helpful. Just for like information, just to increase our knowledge.
From my point of view, this what is it called? So this kind of algorithms are not really important, especially since RCNNs and fast RCNNs are completely something from the past. So basically, you wouldn't be using a fast RCNN neural network anymore, or or an RCNN neural network anymore. So that's why I completely skipped this area. But I guess tomorrow morning, I will give you guys more information about the algorithm that is being used for search in here. And now let's go. If you guys have any questions.
No.
Хорошо. Let me check the paper. Fast RCNN. Yes. I can't find it directly inside the paper easily from just a single read. If you guys see any, let's search, right? Parse topic proposals. Okay, so these are the algorithms that are being used. So they didn't really describe them in the paper here. But since there are some references to these algorithms, I will try to take a look and see what these algorithms are. So first one is selective search. There is DPM and there is this cascade search. I will check them out for tomorrow and just give you a small section about them, right? Search in GitHub. Хорошо. Now let's go to the lab. If you guys don't have any questions already, all right. RCNN, GitHub. You guys have any questions?
No.
Хорошо. Oh, here's selective search.
As I understood, RCNN as a Dropbox for RCNN is computationally expensive, right? This algorithm, or what's the difference between YOLO, for example, and RCNN?
YOLO does not use RCNN.
This is two object detection algorithms, right? No.
Yes. So basically, YOLO is you only look once. So basically, YOLO only looks once at the image, and does the object detection and so object or region proposals and classification at the same time. Whereas the algorithm that we just described, or RCNN families, they are on the other side of families, which does the region proposal first and then the classification first. We will speak about this in more detail tomorrow when we just try to compare Detectron with the YOLO family, right? So basically, these are the two biggest families in the object detection family or object detection area, and we will see the comparisons between both of them. Right?
RCNN doesn't do any object detection, right?
It does do the object detection, but it does it after.
I see. Okay.
Yeah. So first thing it does is region proposals. The second thing it does is the classification of these regions. Whereas YOLO does both actions at the same time. We will see this tomorrow in the architectures of different YOLOs, and they're actually very simple to use.
Thank you.
Do you guys have any more questions? The lab is going to be a very simple lab. Yes, here it is. So basically, I'm going to give a tutorial or like a talk in a couple of days on how to train YOLO v4 or object detection models on for a task such as detecting the empty slots inside what is it called, inside a parking lot. And I decided to just use this example for you guys for the training. We will also take a look on how to train Detectron, and we will take a look on the architecture of Detectron or the components of the architecture of Detectron. If we have enough time, of course, because if we don't, then we just do it tomorrow morning the first time, right? The first thing in the morning. So the goal of this lab is just to get you guys to build a model that can perform this task, right? Before we get started, you're gonna have to understand that classification and object detections are very different fields, right? Classification is something that you can easily do on any laptop, on any type of hardware, without really knowing the hardware you are running on. Whereas object detection, it's kind of a hell. So basically, you're gonna need to know, in most cases, all the information required about your GPU, and in some cases, even about the CPU itself, right? So a very important command that you can use is this one. So just checking the version of NVC, and if you haven't installed the correct version of QD8N, then you're probably going to suffer a little bit later. NVIDIA SMI is very useful to give you an idea on what are the different GPUs inside your laptop or your hardware, and it gives you also an idea about what is the CUDA version. This is very beautiful code that will give you in the end this value. So basically, this is the GenoCode architecture and some other informations related to your the architecture of your GPU. And this information is very important for compiling Darknet a bit later on. So this code, you can just you guys can just use it. Here are just a few of the most commonly used GPUs. There are others in here that you can easily add. If you can't find your GPU in this area, then probably it's too old and cannot be used to compile Darknet. If you want to check, I think there are some. Just Google it. Just Google the name of your GPU and follow it with Arch or GeneCode, just the name, and you will probably find a lot of forums which will give you this information. This information is very important because you will be writing it into the config files of Darknet. Now that we understand what are the different values, yes. Do we have such lab in Moodle? No, I haven't uploaded it to Moodle yet. Should I upload it already, or should we go through it?
I think it's only but after the lab.
Let me upload it. Yeah, you are right. Should I upload for example, the lecture slides and the lab before the session or after the session?
I think after.
Okay. Anyone with the link? Done. Quiz. No. Let's here. Right. object action activity lab 3 darknet import. I think you guys can see it now. If you have access to Moodle, you should be able to see this in here.
Yes.
Okay, let's continue. So now, once you have understood your GPU and or your CPU, in most cases you should probably opt out of using anything that is CPU is 32 bits. Use a 64-bit for running it. If you only have 32 bits, we will speak about these things in the end of the course, where we will speak about deployment and these problems, right? The different repos that you can use for, or you can clone to start using Darknet. I would recommend using the Darknet from Alexei AB, or this RoboFlow AI Darknet implementation. So it's just the same Darknet, but they give you just a little bit more files that you can play with to speed up your training, right? Let's open the Mac. Let's start by running, right? Run all, and we will check what are the different files that are inside of Darknet that are used for the configuration. The main file that you should be playing around with is the makefile. So the makefile first gives you this. First, you have some flags, whether you will be using GPU or not, whether you have cuDNN or not, and whether you will be using OpenCV. So these 3 flags, you should always fix them before starting to do the inference or starting to do the training on any hardware. If you're going to do it on Colab, then Colab already comes with pre-configured CUDA and cuDNN and with the correct versions of OpenCV. If not, then you're probably going to suffer a little bit because it's not going to understand the installation of OpenCV from Python. So you're going to have to install OpenCV either from source, or you're going to have to preferably compile OpenCV on your own. And provide the path to the compilation using environment variables. So this is a bit of a tricky work if you're going to train outside of Colab. But if you're going to do it on Colab, then most of these values are set by default already for you. The second thing, the second part, which is very important, is this one. So the architecture value. Just go here, and wherever you find your output, just put it in this area, and you should be good to go. Again, inside the makefile, they will give you some hints on what architecture you should be using depending on your GPU, but most cases you will not find your GPU inside their makefile, so just look for it on Google and you will get your answer.
May I please repeat one more time about Arch, what this means?
So basically, this is just some, what is it called? So some parameters of your GPU, the architecture of your GPU. I'm not really sure what these parameters are about or what are they, what are their significance, but usually they're just parameters of your GPU that you can find online, right? This is very useful because it helps Darknet, it helps Darknet understand what kind of libraries should it be using, what kind of versions of each libraries should it be using. As you guys definitely know that this is going to be done, or the calculations are going to be done on the GPU directly. So understanding the architecture and understanding all of these things is very important to compile the code. Yes, so once you have checked, or once you have changed these values to your corresponding GPU, just run this make operation, which will create the different scripts for you to run, right? Once it finishes, you should have something like this, some very ugly output like this, but that means it did a good job. The second step is to download the weights of the model. And to do this, I would like to just come here to the Alexey IB repository. So Alexey IB is the guy who made YOLO before. He's a Russian guy, as far as I know. I think he's working in Moscow or something like that. Let's check again. Yeah, he's working in Moscow with Intel. So basically, he's very famous for his YOLO v4 model and his scaled YOLO v4 model, right? That one really gives very good results. And this is the implementation. So this is the GitHub repo. It does come with a very, very extensive README that is very difficult to read if you are a newbie. So that's why I decided to go with the RoboFlow implementation, since it's easier for quick starters. But once we understand the different algorithms and the different values for configuration and stuff like this, then you should always just use this implementation directly of Alexey AB. A very important part inside the Alexey AB README is this pre-trained models part. So first, let's understand what are the different YOLO v4s that exist. So here we can see a comparison of different YOLO v4s versus YOLO v3. So you can see that here is the, let's say, the accuracy. We will speak about what is average precision later on. And here is the frames per second processing, right? So here you can see the bigger, the better. So this is in the real-time area. If you can process more than 130 frames per second, then you are very fast. And you can see that, yes, so you can see that YOLO v4, it makes a very good balance between accuracy and speed. And we can see later on, not in this chart, but in other charts where he will speak about YOLO v4 and YOLO v4 scaled, you will see that it does provide even better results than this one. So here we see, for example, the YOLO v4 with different image sizes and all of these information. Yes, now let's go. 1 second. We go to the configs. Now, if you would like to choose which algorithm would you like to use, the good thing about this implementation is it already comes with various model architectures for you to use. They're already here. They're already, let's check, for example, YOLO v4 custom. So this configuration would give you the hyperparameters of the neural networks, and it would give you this. So basically the architecture of your model, the activation functions, the stride of the convolutions, and all of this information in here. All of this is done for you inside these configs. Usually what you should do is select which algorithm, which one of these algorithms you want to use, and go for it. So here we can see that there is YOLO v4 CSP. There is the YOLO v4 custom, which is the normal YOLO v4. Using this one or this one is kind of the same. There is YOLO v4 Tiny 3L and YOLO v4 Tiny 3L, YOLO v4 Tiny Custom. Using any one of these is very good, but I find that YOLO v4 3L, Tiny 3L does give better results. But for this lab, we will be using the tiny version. So basically, you can imagine that there are different versions of YOLO v4. So there is the smallest model, which is the fastest model, but it's the, doesn't give the best results. There is the custom version or the normal version, which is like the balance between speed and performance. And then there are the like extra large or the large architectures, which take a lot of time, but they definitely give you better results. So yeah, before starting to train any model, you should start with the config file and the pre-trained weights of this architecture. Where do you find the pre-trained weights of this architecture? You should come to this README. It's a humongous README. Come to this pre-trained models area and try to look for your model architecture. So here we have the YOLO v4 architectures. We have the YOLO v4 for XMISH, YOLO v4 CSP, YOLO v4 config is the default one. And there's this one that interests us, which is YOLO v4 tiny. Here you will find some information about it. So just the FPS on different GPUs and the performance. This is the weights file. So what you should do is find the path to this file and download it. Sorry, here, yep. So basically here what we just did is we downloaded the weights for YOLO v4 tiny. In some cases, you might not find the weights or the, what is it called? Yes, the weights for your model. In this case, this guy, this is going to be a very tricky one, okay? So let's see, not tags, the different versions, releases, yep, there they are. So basically you would have to go to each release and check inside the, yes, assets. Yep. Here you will also find the assets of different releases. Of course, sometimes you will find your weight file in here. If you can't find it here, go to the next, to the previous release. If you can't find it, go to the previous release. If you can't find it, go to the previous release. So again, either you look for it inside the README directly, or you look for it inside the release section where you go through the assets and look for the architecture that you want to find, right? So now that we have seen the Alexei IB repo, we understand that there are two main things that we should focus on before training or doing any of this, or before looking at the data even. We should focus on which config or which architecture are we choosing and what are its corresponding weights. The bad thing with the YOLO v4 or this implementation of Darknet is that if you use wrong weights file, it's not going to throw an error. It's not going to tell you that these weights are wrong, but it's just definitely going to just ignore the weights that do not correspond to the config, and you will be retraining from scratch and your performances are going to be very bad. So it's very important to find your correct config file and its correct weight file, right? Corresponding weight file. Nice, let's go back. So here we have downloaded the correct weight file. There is another one, which is this one. I think this one is the file that you guys can find through the releases, and this one that he puts in his README. We can download both. For data formats and data sets, I recommend using RoboFlow. So RoboFlow is a very simple application that, or a simple website that allows you to host your data set in one format and then download it in all the different formats that exist. We will check what RoboFlow is and his public data sets that already exist. Yep. Yeah, so these are all data sets that I have. No. How do you log out? I think this is the logout button, right? Yes. Yes. Public dataset, RoboFlow. And here are the public datasets that RoboFlow comes with. So there's this aquarium dataset where it gives you some bounding boxes of different animals inside the aquarium. There is this chess pieces dataset. It gives you the name and the location of the chess piece inside the image. There is this one for red blood cells, I think, or viruses. There is this one for raccoons. Well, a variety of datasets. I chose to use this one. So PKLOT dataset, because it has a lot of images and it's still something that you guys can train quickly, right? So basically, come here in the dataset. We can preview some examples. So here are the examples. So as you can see, this is the example images that they have, the annotations. there are lots of annotations in here. And here are the different formats for different models. So the problem with what we just described earlier, where you can represent a bounding box in different ways, this created all of these different formats. So for example, this format uses a specific annotation format. This one uses a different one, different one, different one, different one, different one, different one. So all of these different formats exist, and every model only understands the format that the researcher used for training it. What we will be using is this one. So the YOLO darknet TXT format. Come here. Yes, continue, show the download code. And basically copy paste this code into your Colab. Here it is, curl. It will download it, unzip the file, and then just remove the zip file. Nice. Once we have the data set, now we'll start looking at the data structures. So the data set comes in, again, different formats, different data formats come in different data types. There is another data type which is very interesting, which is this one, TF records. So TF records are very good if you're going to be using TensorFlow, but I don't recommend using TensorFlow for object detection unless it's a constraint that you have from the industry or something like that, right? Just want to make sure why there is a problem here. It's busy. I think I'm having some problems with the internet. Managing sessions. Let's close everything. It is still saying it's busy. Let's change to this one, for example.
How many Gmail accounts do you have?
Oh yeah, I have a lot of these because usually if you're going to do some research, we're gonna need to do a lot of computations, right? And having different Colab notebooks running at the same time is very important. So basically I have like just random Gmail accounts for running this boy again and again. Let me just close everything I have because my laptop is screaming right now.
Yeah, but new Gmail accounts don't get privilege of using good GPUs.
Really?
Yes. Usually, if you have, if you don't use Colab so often with with one Gmail account, it doesn't give you like a fast GPU as the one you already use with frequently.
Oh, I didn't know that.
I tried to do this for a project, and I found that this is actually, I have two Gmail accounts. One I use it frequently. It gave me like good GPU. The other one was really much slower.
Oh, I didn't know that. For me, all of them actually gave the same kind of overall performance.
Maybe you're lucky, but it happened with me a couple of times.
So let's check here. So for example, this is Tesla T4. Yeah, it's good. Yeah, sometimes they give you, I wouldn't say, I'm not really sure if it's dependent on the, what is it called? On the Gmail that you use. Because even with the same Gmail, sometimes they give me different GPUs, you know? I think
actually, like Google actually explained this feature of the system. Actually, we have multiple GPUs, and actually we distribute in a manner of priorities. And actually, they analyze how you use the Colab during the same time, during your Google account. And actually, if you're using it intensively,
yes,
they lower your priority, and most of the time you will access to the very slow GPUs.
Okay,
but if you register a new account and going to buy a new account, this account having like a history of usage of Colab, actually they prioritize you very well, and you may get up to like VSTO if you want.
Got you. Nice. Well, that's a good information to keep in mind. Now let's check the data set, right? So we've downloaded the data set. We cloned the darknet repo. Here are the different configs that you should be taking a look at. There you go. Inside each config, you're going to find the batch size, the subdivisions, the height, width, number of channels, momentum, this is for training, saturation, exposure, hue, learning rate, burn-in, max batches, policy, steps, and scales. The most important things you should check in here are the height and width of the model. These height and width should correspond to the same height and width used for training your pre-trained model that you will be using. Another one very important, of course, is the learning rate. Max batches, in this case, is the number of epochs that you will be using. I don't know why they called it max batches, but it is what it is, right? So basically, this is the number of epochs that you will be running. And the number of steps, usually you should configure these two steps as the 80% of max batches and 90% of max batches. We can check this in here in the GitHub repo of our friend Alexei IB. He provided a very good explanation of every single one of these algorithms, every single one of these hyperparameters, and how can you tune them, right? There it is. Dun, 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 dun. It should be right here. Not this one. We'll go to this one a bit later on. Should be in the beginning somewhere here. Nope. This one's for these. Okay. Yes. Yeah, here you go. The max batches should probably be something like the number of classes that you have multiplied by 2000. So for example, if you have 7 classes, you should have 14,000 batches, or the number of epochs, and so on and so forth. And it should not be anything less than 6,000, right? And then you change the steps line to correspond to 80% of the max batches, which is the first value, and then 90% of the max batches to the next in the second value. This is just used to save different versions of your model while training. So basically, once the model trains 80%, we save it. And once it trains 90%, we save it. Once it fully trains, we save its versions. So basically, you will be saving different versions of your neural network. This is something that's going to bother you guys a lot, which is changing classes equals inside the config file. So basically, let's go back to the config file here. Yeah, we can't see it. Let's come and see it here. Config. Yes, YOLO v4 tiny, for example. In here, you're going to be changing these things. First is the classes equals. This one, you must change it to the number of classes that you have. And every time you change a classes equals inside a YOLO function, the previous convolutional operation, the number of filters inside of it must be changed also following this formula. We will check the formula right now. Yes, here we spoke about changing the number of classes, changing the height, changing the classes, and now changing the filters. So you're going to have to change the filters to classes plus 5 times 3 in every convolutional operation that comes before a YOLO layer. In our code in here, we've done it in a more elegant manner. So basically, we just read the data set. We take the information about the number of classes. We get the information about the maximum batches. Step equals 1, steps 2. This is, we convert them into a string. And this is the number of filters. And what we do is we go through the, what is it called? We'll go through this config. There you go, you see it. And we kind of change it manually like this, you see? And for, as we said, the classes before value, where is it? YOLO layer should be close by. Here's, yes, so classes equals number of classes, filters that come before the YOLO equals the number of filters. Now that we understand how the config files work, its structure, and how can we change it, let's go speak about the data, right? In the data, we have, of course, different folders for training, testing, and validation. Let's go for the validation part and see its values, right? So the first thing you'll see is there is a file called darknet.labels. We can open this file here. Oof, it can't even show, right? Inside this darknet.labels, you're just going to find the name of your labels, right? And these files will give you the following: the image, so a JPEG file of the image,
the coordinates,
and the bounding boxes. For some reason, it is dying right now with training, so it's not showing us the data correctly. We can solve this problem by what? Let me see. Let's do it locally, right? I'm going to download the data. There it is. So with each image files, each image file, you're going to find a corresponding TXT file. Every line is going to be an object. The first number of the object is going to be the class index. The second one is going to be the coordinates of, so the second, third, and fourth, and second, third, fourth, and fifth values will be the coordinates of the bounding box. You can see that these coordinates are not real coordinates, but they are normalized according to the height and width of the image. Now, to understand what these coordinates are, we should come just here in his documentation and understand what kind of, it should be here somewhere. Not here, so it's downstairs a little bit here. Classes, nice. Yes, so basically object class, the X coordinate of the center point, the Y coordinate of the center point, and then the width and the height. All of these numbers will be between 0 and 1 since they are relative numbers to the height and width of the overall image, right? There we go. So basically, this is the interpretation of this TXT file that comes with every image. Once we have the data set like this, we leave it. Now we go to the config of the data set, and they are usually in this folder called data. Just to make sure that I'm checking the same folder, the same file I'm using here. Yes, so object.names and what else? There you go. Sorry. Here. This is going to take a lot of time to show. Object.data. It is taking too much time. I'm not sure if it's a problem with my laptop or with Colab. Anyway, let's check the values which are already here, and later on, once they are from our data, we will check them out. So coco.names, for every data set, you're going to have a file called dataset.names. This will be just the names of your different classes, right? And basically, if you have in a TXT file 0 and then the coordinates, that means this object is a person. If you have, for example, 7, then it's a bus. If you have train, then if you have if you have 6, then it's train. If you have 5, then it's bus, and stuff like that, so on and so forth. The other file that you should be configuring is the dot. Let me find it. Can't find it. Yes, object.data. I hope it can open. Yes, in the object.data, you will basically just provide the path to your data set. So backup is where you will be saving your trained model. Names is the variable which will contain the object.names, which are the names of your classes, space empty or space occupied. And then the train and validation will contain the list of images for the list of images that you will be using for training and the list of images that you will be using for testing or validation. If you want to have a test, then test equals, for example, if we have this file, test.txt. Inside this train.txt and text, okay, there we go. Yes, I hope I can open these quickly. So it's basically just the path to the images of your training and testing, you see? Again, in this file, you do not put the path to the txt files. The path to the txt files is just basically this one, .txt. So basically, you don't specify it, and YOLOv4 and Darknet will be looking for it automatically based on the name of the image. And that's it. Once you set up, so basically your config file to make sure that you're using the correct model architecture with the different hyperparameters that you choose. So you can have different values here. You set up also your object.names and your object.data. Object.data contains the file paths and the number of classes. Object.names just contains the names of your classes. Train.txt, validation.txt, these are files that contain the list of, what are they called? The list of images. And the last but not least is the txt files that come with every image, which contain the labels of that image. Once you have all of this set up, the training will be very simple. So the training is the following line of code. And I think it's because we are doing the training that my laptop is now suffering. It's because this data set is quite big on images. 0.
But you're counting on collab. How is your laptop is suffering?
Ah, you see, because I am doing these output. So basically, this output is still happening on my. There are some still calculations which are happening on my laptop.
You mean JavaScript?
Yeah, in JavaScript. That's why the laptop is like, who does calculations in JavaScript? I'm gonna stop it right here and just change the max batches into a very small number, right? Interrupt execution. Should be interrupted pretty quickly, right? Yeah, it was interrupted. Let's check if there's something in the backup. Yes, we will be using this backup. What we will change is simply this, right? The number of max batches, let's make it to 100, right? This is not enough to train a model, but it's just enough to see something happening, right? To see the training. Let's confirm that the change was actually made. Here we see max batches equals 100, right? And then steps equals 80 and 90. So the changes were correctly made. And now we will not be using this file as the source of pre-trained weights. We will be using the following, right? Backup, custom. So basically, we'll just continue training from where we left off before, right? It didn't do the training. Why? Or did it do it too fast? Yeah. Okay, I think 100 was too quick. I want to see some output also. Let's make it 1000, right? There we go. The first thing it will do is basically it will check everything with the thingy, with the architecture of the GPU, and then it will start reading your weights. So here it's drawing the layers of the neural network, and then it will be loading your weights in here, I think. Yep. Done, loaded, yes. So then it will start loading your layers from the file. Sometimes, if you're lucky enough, you can still be able to read some messages in this area saying that there were some layers that were, for example, ignored or something like that. If you see this before it gets deleted, then you should probably go and fix the pre-trained weights that you just chose, right? And then it will just give you the training. So this is just the different loss values, how much time is left for the training, and usually it will give you the MAP calculations. So you can think for now, MAP, think of it as just an average of the intersection over union of different values, right? So for now, it's just the same thing as intersection over union. We will speak about it in more detail in tomorrow's lecture. We will describe how do we calculate MAP and these values. We should finish the training soon. Now it's calculating the MAP, and it will give us, there are lots of images in this data set, huh? I think there are lots of images in the validation even. Do you guys have any questions so far?
So we will cover tomorrow the mean average precision.
I didn't understand your question.
Will we cover tomorrow mean average precision?
What do you mean? I didn't get the question.
Will we cover MAP tomorrow?
Will we cover or where will we cover?
Will we?
Will we?
Are we going to?
Yes, we are going to cover different, what are they called? Different ways of metrics of evaluating your object detectors. So for example, recall, F1 score, and precision are very important for you, for your model. There's the average, yes, even more so than MAP. So a lot of people tend to focus a lot on the mean average precision score of at 50, 0.5 threshold. But I personally like to focus only on F1 score. So F1 score is the best way or best method, is the best metric to understanding if your model has correctly trained or not.
And in this case, it is weighted, right? So you need to weight F1 because you have multiple classes.
We will speak about these things tomorrow, and I think we will. How much time do we have?
No time. We need to go to rest.
So basically, now if we want to do the inference, we can just specify any input, any image. Let's check, for example, some image. Let's check some input image from our data. Image path. There you go. So basically, this is how you run your model. So basically, darknet detect. You always have to have the config file with you. Even in inference, you always have to have the, of course, the weights of the neural network of the model. And here you will have the image path, right? So which one do you want to use? And it will give you the following results. It's not perfect. So basically, there is a slot here that it didn't predict. There's a slot here. There's a slot here. But that's mainly because we didn't train it well enough. This data set contains a lot of images, which is amazing. Hence, you can easily train the model for even a bit longer than 2000 times 2, which is just 4000. You can easily go ahead and train it for, I don't know, 8,000 or 10,000 because you have enough images and it's going to give better results. Just to quickly wrap up everything we have done so far today, or at least in the lab. We have seen how to get the different values of the neural network. We have seen how to clone and change the make file in order to make or to compile the darknet. Where can we find the different pre-trained weights for our chosen architecture? In here, it's true that we have a perfect data set with all the files already configured. In most cases, you're gonna have to you're gonna have to change the format of your data. Sometimes it's gonna come in XML files, sometimes it's gonna come in JSON files, and you're gonna have to change all of these files into the corresponding TXT files and the formats used accordingly. We have checked what are the contents of object.names, which are just line by line the names of your classes. We have checked the object or data.object, object.data file, which contains just the paths to different variables, to your different files for the data set for this one and for the backup. So this is just how you can configure the custom.csv CFG. Don't forget to change the number of classes and the number of filters correspondingly. And for the training, you're going to have to send in your object.data. So this one just provides the access to the class labels, provides access to what is the training, what is the validation, and provides the access to the place where we will be storing our output models. We also provide it with the config, and we provide it with the weights of training. There are a variety of different, what are they called? Of different, help me out. Of different flags that you can send to the training function. So sadly, since we restarted the training again, so you can see that this chart is quite useless. But if you start the training from scratch and do it correctly, then you should probably have a chart similar to this one. This one is also empty. So basically, you should have a chart where you have the loss function going down and the MAP score going up. This is how you do the training. For inference, it's very simple. So basically, you call darknet with the detect flag and basically give it the config, the weights, and the image that you would like to find. So thank you guys a lot for staying until now. I think it's 9 at your place. If you guys have any questions, we can cover them now. If you guys want, we can cover the questions tomorrow morning.
I think it's better to cover the questions tomorrow.
Yeah, I understand.
So here just simple question: why do we use Darknet and not PyTorch?
Why do we use Darknet and not PyTorch? For the same reason, for example, we don't use TensorFlow, because it's not very flexible or not very easy. Sadly, the PyTorch implementation is not something that you can run on most of the servers that you can find. So for example, servers of Innopolis, I've worked with the servers of the machine learning lab and the servers of the industrial AI center. And you can never run this version of, you can never run PyTorch with that version for YOLO v4 on these servers. Same thing for me in France in here. It's always a pain to try to run PyTorch v4 or even the PyTorch v5, PyTorch YOLO v5 implementation, which is the best implementation out there. But it's still not going to be something that you can easily do on different architectures. The Darknet implementation is definitely the fastest and the thing that you can easily deploy and train on different kinds of hardware.
Well, thank you.
You're welcome. But we're definitely going to check the PyTorch implementation tomorrow.
And small note about the timing that we have actually, like, according to the schedule, if we have 2 lectures at the Friday evening, we need to start at 17:20, but we start at 6. This why according to the schedule we have 40 minutes ahead. Yes, and actually we need to finish at 21:10. But actually we have no breaks during our 2 lectures. This why by this shift we need to end exactly at 9. Just for your information.
Got you. So I will